Amid the endless blackness of the cosmos, immense whorls of brilliance come into existence. But why do they assume this distinctive configuration? What keeps these forms intact across billions of years? And what eventually causes this remarkable order to unravel? Spiral galaxies stand among the most fascinating and puzzling architectures in the entire universe. Nearly 70% of all charted galaxies exhibit this remarkable pattern. What imposes this structure upon them? Is it the force of gravity, the unseen influence of dark matter, or perhaps an unknown phenomenon we are yet to uncover? These vast whirlpools of stars, gas, and dark energy spin with extraordinary accuracy. Still, the concealed mechanisms that govern their existence continue to mystify even the brightest minds in astronomy. Together, let us venture into the cosmic abyss and try to decipher the secret behind their captivating symmetry. So, what precisely is a spiral galaxy? At its core, the explanation is quite direct. Spiral galaxies are systems marked by ordered arms, prominent clusters of stars, and thick clouds of interstellar gas, all arranged in a flat, disk-like formation. Despite their abundance, the underlying causes of their emergence and the persistence of their structure remain subjects of intense scientific debate. Spiral galaxies are not uniform. They display a rich spectrum of designs. A few systems showcase sharply defined mirror image arms, which astronomers call grand design spirals. Others appear more chaotic, featuring numerous arms that are hard to distinguish and count. In some cases, a bright bar bisects the galaxy, from which spiral arms extend outward. The presence of these bars indicates that the internal movements and evolution of galaxies can vary dramatically. The distribution of color within spiral galaxies reveals further secrets about their stars. In certain galaxies, the arms shine with the blue light of younger, hotter stars, while in others, older, redder stars predominate. These distinctions point to different histories of star formation and a variety of conditions at play within each galaxy. Additionally, galaxies that seem spiral at first glance may display oddities brought about by nearby cosmic neighbors. When galaxies interact or undergo minor mergers, gravitational forces can twist or warp the spiral design, sometimes creating unusual hybrid features unseen in solitary galaxies. Tracing back through history, these cosmic structures were first known as spiral nebulae in the mid-19th century. Early astronomers observed their swirling shapes without realizing their true distances. In the 1840s, William Parsons, the third Earl of Rosse, became one of the first to record their characteristic spiral appearance, notably observing the object later named Messier 51. At that time, such objects were not yet identified as galaxies themselves, but were labeled nebulae, a term for any faint, fuzzy celestial phenomenon. Almost 100 years later, in the 1920s, everything changed. Astronomers confirmed that these nebulae were not just components of our own galaxy, but vast, separate islands of stars. Thanks in large part to the careful observations and insights of Edwin Hubble, it became clear that these spiral forms resided far beyond our Milky Way. This revolutionary discovery dramatically expanded humanity's sense of place in the universe, revealing our galaxy as only one among countless others. Yet, as scientific understanding advanced, researchers encountered a dilemma known as the winding problem. Upon realizing that stars within a galaxy do not revolve as a single solid mass, but rather orbit at varying rates depending on their distance from the galactic center, astronomers faced a troubling puzzle. If the components of a spiral galaxy spin at different speeds, why do the arms not wind ever tighter and eventually vanish? Early propositions suggested galaxies might rotate as rigid bodies. However, later studies demonstrated that stars nearer to the center complete their revolutions much faster than those at the outer edges. This ongoing differential rotation should, in theory, have caused the spiral arms to wind ever tighter over billions of years, which clearly conflicts with what astronomers actually observe. Rather than becoming more compact, the arms remain broad and persistent, prompting a profound inquiry into what forces are at work to maintain their shape. Numerous hypotheses have emerged to confront this mystery, each offering a perspective on how spiral arms form and endure. Among the most widely recognized is the density wave theory, put forward in the 1960s. In this framework, the spiral arms are not conventional material features, but rather zones of heightened density sweeping across the galactic disk. Stars and clouds of gas entering these denser corridors experience a brief compression, which can ignite bursts of starbirth. The originators of this concept liken the phenomenon to a traffic jam on a busy road, where the congestion moves along, but each individual vehicle continues on its path. While density waves account for the balanced patterns present in many spiral galaxies, they leave open the question of what initiates and sustains these waves across cosmic time. A different viewpoint centers on a process called self-propagating star formation. From this angle, stars are born in compact clouds of gas, and the powerful shock waves unleashed by supernova explosions can spark the birth of new stars in nearby regions. This cascading effect can give rise to loose, irregular spiral structures. Such formations, often labeled flocculent spirals, tend to lack the symmetry and durability described by the density wave model. Although this mechanism explains the scattered look of certain spiral galaxies, it falls short when it comes to accounting for the strikingly regular, grand design spirals that dominate the cosmic landscape. A third notable model, swing amplification, proposes that very minor disturbances within the disk, perhaps arising from collisions between clouds of gas or gravitational tugs from neighboring bodies, can become dramatically enhanced as the galaxy rotates differentially. These initially tiny ripples can transform into pronounced spiral arms. However, computer simulations suggest that features produced by swing amplification may not last long unless they are continually replenished by fresh disturbances. This theory, therefore, ties the emergence of spiral arms to the inherent instability of a spinning disk, but does not entirely resolve the issue of why some galaxies display spiral arms that persist for eons. Taken together, these theories make one point unmistakable. No single explanation fits every spiral galaxy observed. The diversity of spiral patterns instead implies that multiple processes might be influencing galactic evolution at once. Technological progress has allowed astronomers to gain fresh perspectives, but it has also brought forth additional puzzles. Researchers now depend on observations across many wavelengths to unravel the mysteries of spiral galaxies. Optical images reveal where the youngest stars are located. Infrared views, which can see through cosmic dust, often expose the hidden skeleton of a galaxy, while ultraviolet photographs spotlight regions teeming with newborn stars. One spiral galaxy might appear perfectly organized in the infrared, yet fragmented and chaotic in visible light. Such differences arise because varying wavelengths interact differently with dust and gas. Dust can mask older stars while highlighting regions of stellar birth, thereby making it more difficult to discern the galaxy's true architecture. Beyond multi-wavelength imaging, spectroscopy yields even more information, revealing how stars move and what they are made of within the spiral arms. Even so, the absorption of starlight by interstellar dust and the intricate overlap of countless star spectra continue to frustrate astronomers as they strive to piece together a comprehensive understanding of spiral structure. Investigating the spiral patterns found in galaxies beyond our own offers the benefit of an unobstructed external vantage point. Yet, deciphering the structure of the Milky Way comes with its own distinctive set of challenges. Since we reside within the galactic disk, it is impossible to observe the Milky Way in its full grandeur. The precise count and layout of its spiral arms remain subjects of passionate scientific debate. While certain research points to the existence of 4 main spiral arms, other findings contend that only 2 of these arms are clearly delineated, with the remaining features representing minor branches or spurs. The question of whether a central bar exists within the heart of our galaxy is another matter of ongoing discussion. Breakthrough observations from cutting-edge space missions, most notably the celebrated Gaia Astrometric Initiative, have shed extraordinary light on the locations, motions, and luminosities of close to 1 billion individual stars. Nevertheless, even with these advancements, analyzing and making sense of such a colossal volume of data remains an intricate and demanding endeavor. Recent studies have even cast doubt on some of the previously accepted models concerning our galaxy's spiral configuration. Within this landscape of conflicting theories, computational simulations have long served as a critical tool in probing galactic dynamics. Early modeling efforts relied on stripped-down frameworks, focusing exclusively on gravitational forces between stars. These initial computer experiments seemed to bolster the density wave hypothesis, which posited that spiral formations could arise spontaneously from the gravitational interplay in a spinning disk. Over the past several years, however, leaps in computational power have allowed scientists to craft simulations that incorporate a spectrum of influences, ranging from the behavior of interstellar gas, the birth of new stars, the feedback from supernova, to the intricate exchanges between stars and the surrounding interstellar medium. Such comprehensive models frequently generate spiral arms that prove to be fleeting or unstable, particularly when every nuance of physics is modeled. Researchers have discovered that simulation outcomes can differ dramatically based on starting conditions and the level of detail in the models. Simulations employing a sparse number of particles tend to show spiral arms as ephemeral and chaotic. On the other hand, simulations with higher resolution, utilizing a far greater quantity of particles and more intricate physics, have demonstrated that, under certain parameters, robust and enduring spiral arms can indeed take shape. These sophisticated modeling efforts have illuminated the delicate sensitivity of spiral structures to a host of physical conditions. It seems that the formation and stability of spiral arms depend on a combination of factors, such as density waves, localized gravitational instabilities, and outside disruptions. Contemporary studies increasingly support the notion that there is no single, universal answer to the mystery of galactic spirals. Rather, a blend of mechanisms likely operates together or takes precedence depending on the circumstances. In galaxies with beautifully symmetrical spiral arms, density waves may exert the dominant influence, while in others, the patterns of star formation and unique rotational characteristics might play larger roles. The sheer diversity of spiral patterns seen throughout the cosmos points to the interplay of many forces. In certain cases, the gravitational tug of neighboring galaxies can set off or alter spiral forms. In other instances, internal factors, such as local gravitational instabilities, take the lead. The powerful synergy between multi-wavelength observations and advanced simulations continues to shed light on these cosmic structures, though many mysteries remain unsolved. Looking to the future, missions such as the Nancy Grace Roman Space Telescope and Euclid, together with ground observatories like the Vera C. Rubin Observatory and the Extremely Large Telescope, promise to greatly enhance our understanding of spiral galaxies. These cutting-edge tools will deliver detailed, high-resolution data across multiple wavelengths, paving the way for in-depth investigations into the movement of stars, the distribution of dark matter, and the complex dance between galaxies. In the coming several decades, remarkable advancements are anticipated to shed light on major unresolved questions about how spiral structures are formed and transformed. These innovations will yield invaluable information for theoretical models that strive to interpret the vast architecture of the cosmos. Importantly, delving into this topic surpasses the study of individual galactic patterns. Gaining insight into the mechanisms behind the creation, persistence, and eventual disruption of spiral arms is vital, as these features are key to unraveling the driving forces of galactic metamorphosis. Spiral arms are far from mere embellishments. Rather, they mark dynamic zones where gravitational forces, the movements of interstellar gas, and influences from external sources come together in a complex ballet. This interplay provides essential hints regarding the hidden mass within galaxies, especially the elusive dark matter. The shaping and endurance of spiral arms are heavily shaped by gravitational fields, which in turn are dictated by the surrounding dark matter halo. By closely examining the movement and transformation of these spiral arms, how they coil, intensify, or gradually fade, Astronomers are able to infer details about the spread and concentration of dark matter indirectly. Beyond this, spiral arms are prime locations for the birth of stars. As clouds of gas travel through these regions, their density rises, triggering the collapse of gas and the ignition of new stars. As a result, spiral arms act as natural laboratories for investigating how efficiently stars are formed.
Comprehending the factors that either foster or impede star formation empowers researchers to assemble a holistic understanding of galactic growth and transformation over time. The appearance of spiral arms frequently reveals traces of past encounters. Gravitational pulls from neighboring galaxies or the lingering effects of smaller galactic mergers can warp or spark the emergence of spiral motifs. Such historical imprints are indispensable, as these interactions reshape not only what we see, but also the allocation of both ordinary matter and dark matter.
Meanwhile, with every fresh observation, our cosmic charts become more refined, and our grasp of the universe deepens, allowing us to peel back its secrets gradually, one revelation after another.